Okay, good. Welcome to this session for all attendees of the Design Conference 2022. It's my great pleasure as chairperson of this session to moderate and organize the different presentation and discussion. First, we will have the video of all presentation, and in the second time, we will be able to debate, and attendees will have the opportunity to ask questions to the presenters or speakers about the work they have done. Then we have in this session 5 papers, if I'm right. It's a British-German session moderated by French guide, and it's a very interesting organization and virtually hosted by our colleagues from Croatia. It's a great enthusiastic opportunity while it is not being in real life in Dubrovnik. Okay, then I suggest to start now the videos, and we have just be sure Fabian Wilking from Friedrich Alexander Université Erlangen-Nuremberg.
I'm here.
Great, thanks. Fabian Laukotka from Hamburg University of Technology. Chris Snider from University of Bristol.
I think Fabian is waiting for the permission to share audio and video. He wrote that in the chat.
Okay. Thomas Eickhoff from Technische Universität Kaiserslautern.
Hello, everyone.
Welcome. And Yannick Koch from Technical University of Darmstadt.
Hello.
Good. And maybe I forgot to introduce myself. I'm Professor Benoit Eynard from Université Technologie de Compiègne. It's a city located at about 100 kilometers in the north of Paris. Then, Jelena, I suggest we launch the video, and in parallel, we will authorize the speaker to connect correctly.
Hello, everyone. My name is Fabian Wilking. I'm a research associate at the Chair of Engineering Design at the Friedrich Alexander University Erlangen-Nuremberg. Today, I want to present you our current research, which is about the utilization of system models for the design and operation of digital twins. I want to start with a brief definition of the digital twin. We mainly focus on the definition of the German Research Association for Product Development, which gives us a common understanding of how the digital twin is defined in the German-speaking area. As you can see here on the right in this figure, which is derived from the definition, the main component of the digital twin is its digital master or its models. These models are used to interpret the operating data, to transfer it into specific simulation results, for example. But if we view complex systems, it becomes very aware that these models are intertwined. The operation data is linked to each other. We don't have like a clear way to go to interpret data. So what we kind of need is like a meta model that describes the behavior, when to run which simulation and how to interpret specific data. We have seen in model-based systems engineering that there is something like that, the system model, which describes the behavior and structure of a system. So we basically asked ourselves the question, well, can we use this kind of model for our digital twin? Can we directly utilize it to define the behavior of our digital twin? And of course, as a generic question, is it possible to compensate any effort by using these models? I want to show you the concept that we used for this. We used a very simple two-stage gear, which we equipped with sensors and data streaming capabilities. We created specific simulation models like FEM simulations to further use this data from the sensors. And we created SysML models that describe the behavior and the usage of the models. So when a specific sensor value is given, call this simulation or other circumstances. We brought this all together in one specific tool, the sensor data, the simulation models, and what is very interesting about this is that the whole behavior, the whole underlying software tool was basically defined within the SysML models. We used the JavaScript export and the XML export, and we only used what was given in these XML files by parsing them. And this tool is very simple. It basically just uses these simulations, which you'll see on their upcoming slides, and gave the user a recommendation of what to do with the system. Maybe to say that here, this is just a very simple concept. It's not really based on realistic behavior of the two-stage gear. We were just looking into whether we can actually use these SysML models to describe the behavior of the digital twin and furthermore of this software tool that represents the digital twin. You can see an overview of the behavior of our digital twin here. It's basically very simple. We have this idle state in the beginning. We then start the usage. In the beginning, we receive vibration data. If the data receives a critical point, we go into this script here where it's receiving additional data, start simulations. We have a machine learning script running. And then basically in the end, it gives out their prediction and their calculated simulation result to the user. This basically all what you can see here, this whole behavior, that's described and modeled in our SysML model. So this is all what the software is doing in the end is all defined by a system model that basically has this behavior structure here. So after finishing this small project of creating this demonstrator, we can definitely say that we have the technical possibility to utilize SysML models. We can use an XML parser to identify specific elements. We use the JavaScript export of the tools. So the technical possibility to further utilize them is definitely given. Next thing is a very big challenge is creating consistent and machine readable models. Was a very big challenge, but it's definitely doable. Results into efforts for the supply chain later, but it's definitely possible to create consistent models to further utilize them for the digital twin. The probably biggest question is whether we achieved an effort compensation, and we can definitely say yes. We basically saved 2,000 lines of code, which was very nice. We had a very clear error identification at every point where we faced errors. We could directly look into the model, into the diagram and see, oh, there's our error that we need to solve that. Which also results in a very clear system awareness. We always knew which elements are connected, where are interdependencies, and what we need to do to fix it. So definitely given. What would be the next steps now are, well, you can model lots of things within SysML. Not everything makes sense. So it's definitely like for further investigation, like what should be modeled and what should not be modeled, and where are other opportunities to model something. And then what has been a very interesting insight is there SysML tool-like approach actually feasible for creating digital twins? It was very, very handy to create these SysML diagrams and directly derive their behavior and the structure of the digital twin from them. So could that be a feasible approach for future digital twin tools that simply just use the creation of digital twins, and then you can directly derive your digital twin from it. And with this, I want to end the presentation and thank you for your attention. And I'm very interested in the further discussion we will have in this session. Thank you.
Hello and welcome to this short presentation. My name is Fabian Laukotka and I'm a PhD student at the Hamburg University of Technology and the Institute of Product Development and Mechanical Engineering Design. Today, I want to give you a brief introduction into our paper, Digital Twins and Product Service Systems, a synergy with challenges and opportunities.
With different research projects and industry partners, my colleagues and I are currently facing two trends. On the one hand, there's the servitization, or the move from pure products towards more service-based products and product service systems. Former solely sold products can get attached with different levels of services to provide an income stream to the manufacturer even after the initial sell. On the other hand, there's the trend towards an increased importance and usage of data in the form of digital twins and its variety of possible applications ranging from monitoring to predictive maintenance and retrofit planning and many more. While working in these research projects and industry cooperations as well as literature reviews within these topics, it becomes clear that there are many good approaches and concepts for both of these trends, and some have already been implemented. Especially smaller teams face challenges when trying to implement said challenges. But let's take a more detailed look into product service systems. Especially with smaller and traditional enterprises or suppliers, we can see that they often get external impulses to move towards product service systems, or at least parts that can be used for them. However, with that, now they have to move from former mechanical to more complex products that include digital or information technology, which is often required to enable these service aspects. As this new domain is new for them, they facilitate a tremendous initial hurdle. A literature review reveals that indeed knowledge and technology are among the most common challenges named regarding the implementation of product service systems. Required adaptations to the processes and the organization itself, as well as uncertainties regarding possible customers and markets being other frequently named challenges. Besides these challenges, companies nowadays tend towards product service systems simply to enhance their accessible market segments. When adding the value chain or different levels of the interaction of the user and the product to the already shown segment of product service systems, we get a matrix. The currently accessible market segment for a company may lie in this area, and when trying to enhance it, said challenges arise and additional knowledge and know-how are required. Some big industries and enterprises are able to overcome these challenges, as can be seen with aircraft engines and their already finished move from sold engine to operability as a service. Smaller enterprises, especially in the field of mechanical and plant engineering, often supply just parts of a more complex product that cannot be seen as separated as an engine from an aircraft. While they also have many different possible applications, these very factors are currently often found to be addressed by the concept of digital twins. So, digital twins may be the solution to provide the needed enhancement to the current market segment. And here we have the synergy mentioned in the title. Progress in the concepts and especially implementations of digital twins will lead to a better understanding that can be transferred to the described situation of product service systems. Likewise, the segment of product service systems represent a whole new range of applications of said concepts. Even though digital twins appear to be a simple solution to this, they likewise have challenges of their own, as again experiences with research projects and industry partners have revealed. As a newcomer to digital twins, one is faced with an ambiguity of terminology like digital twins, shadows, threads, models, but sometimes an ambivalent definition as well as a plethora of ideas, concepts, and highly specific approaches. Besides this overwhelming first step, only a few of them are detailed and shown specifically described implementations. There's no obvious clear framework or path to follow when starting to implement a digital twin in whatever fashion. Instead, it is more perceived as a promised universal remedy with an overwhelming implementation. A literature review again reveals that digital twins themselves face the challenge of data handling, needed and possible model quality, and depending on the application, sometimes real-time sensitivity, data security, and many more. And with more than 4,000 publications in 2020 and 2021 alone, this is a very dynamic topic. However, there are already many good approaches, yet the transferability needs to be improved. An example for a successful move from product to product service system can be seen in aircraft engines. Formerly, after the product creation, the tangible product, in this case the engine, was sold to an aircraft manufacturer or airline. This specific engine stayed within the aircraft and was maintained from time to time. With the integration of digital twins of the engine, the status can be permanently monitored and the sold product moved from the engine itself to operability as a service or predictive maintenance. To transfer this path from an individual aircraft component to a highly integrated industrial valve that is part of a bigger plant is not easy, but some similarities can be drawn. Currently, the manufacturer of said valve can sell it and, if needed, maintain it from time to time. If the valve can be smartified to be part of a digital twin, as is currently done in a research project of ours, again, other services like pay-per-use or predictive maintenance become possible. While both cases require different implementations, both of them need elements like sensors, data transfer, storages, etc. These common elements can be generalized into a more generic digital twin that then will improve compatibility between products and, with a more common understanding, improves the adaptivity. This can also be then the base for a framework that can assist new enterprises entering the field of digital twins and allow them to ease the challenges that others have already solved. Admittedly, with just 7 minutes time, this was a very brief introduction, and the paper itself represents parts of the mentioned work that is also still ongoing. But to conclude, I've presented digital twins and product service systems as two rising topics. In both of them, we can see that there has been progress in the past years, but mostly very specifically focused. Smaller teams face huge challenges in trying to adapt their ideas. The idea of a generic framework to improve the common understanding of the diverse approaches was named. Lastly, on a more philosophical level, keeping the bigger picture in mind every now and then, instead of deeply focusing on a specific problem, would benefit the whole community.
And with this, I want to finish my presentation and thank you all for your attention, and please feel free to ask any questions regarding this paper.
Prototyping is inherently physical and digital, with designers required to work across both domains to reach their desired outcomes. Prototypes that designers use in each domain vary greatly, with a wide range of physical and virtual models that replicate and test product behavior. Each type of model will have its own benefits, and it typically falls to the designer to maximize these while also balancing cost and fabrication time. These strengths are largely bounded by the domain of the model. For example, digital is fast, reconfigurable, and flexible, while physical is tangible and accessible, but often at a higher cost. Interestingly, these benefits often fall counterpoint to one another. Where one domain excels, the other often has weakness. Taking a workflow perspective, we typically see iteration between the physical and digital as design progresses. This iterative process introduces several challenges, including the time and cost of transition between domains and the challenges of maintaining learning across many disparate models. Given that prototypes for a single product can number in the hundreds, we can infer just how high these costs may be. This cross-domain workflow raises the research questions of this paper and our wider work. How can prototyping workflow be structured to maximize benefit and minimize cost? And can physical and digital prototyping be better integrated to simultaneously leverage the benefits of each? Recently, there has been a huge amount of relevant work in this space through the paradigm of digital twinning. Digital twinning aims to create a real-life digital replicant of a physical system to as high a fidelity as viable, which is then used to perform multi-physics simulations of system behavior. Outputs are used to understand and optimize the physical system, creating learning action loops that improve system performance. This paradigm has already realized benefits across the engineering sector, particularly in production and operational lifecycle phases of high-value machines. However, research has been sparse in earlier lifecycle phases, including in prototyping activities. Looking again at the workflow over time, we can see why this may be. In theory, a digital twinning workflow comprises persistent virtual and physical entities with real-time data transfer between each to allow their parameters to be synchronized. For this workflow to be viable, both digital and physical entities must then exist, be persistent, and be fair reflections of each other, such that parameters may be meaningfully updated. This is not always the case during prototyping. While many models are present, they are not persistent over time, meaning comparable counterparts don't always exist. Rather than create complete digital replicas of physical prototypes, digital twinning for prototyping raises the question of how prototypes across domains may be integrated to streamline processes and support learning. By creating integrated physical-digital prototypes, the learning action loops that are so critical in prototyping may leverage both physical and digital models simultaneously, reducing the quantities of distinct models that we require and allowing designers to leverage the benefits of each at the same time. The recently maturing domain of immersive reality is the key to this capability. These technologies aim to seamlessly link the digital domain with the real world, such that the digital may be interacted with physically, and the physical may be augmented with digital information. The real-time data connections that these technologies create enable rapid learning action loops that cross the domains. In this work, we want to more broadly understand the potential for cross-domain workflow in prototyping. Looking across 4 cases, we investigate implementation and value of the use of immersive realities to support design. To allow us to understand and compare cases, we first formed a framing to describe integration. In addition to considering the integration of physical and digital models, this framing includes the interaction of the designer with the integrated prototypes. Prototyping is a bidirectional learning and iteration process, and as these technologies have different levels of interactivity, it is important to consider both their transmission of information to the designer and also the way in which the designer then passes information back. Using these dimensions of integration, we characterized 4 cases of integrated prototyping workflow and compared them to current practice, in which all models are typically separate with little to no integration. The second case was Protobooth, a physical prototype digitization platform developed at NTNU. Here, the level of integration is fairly low, but the system does allow some intersection between physical and digital through automated information capture from physical models. The third case was CityBlocks, a Lego-based physical city building platform that creates a full-scale virtual reality replica for users to explore. This system kept boundaries between physical and digital, but begins to leverage the benefits of synchronized domains to increase learning while using accessible media as the main interface. The fourth case is a digital mirror, where an editable physical prototype is mapped in real time to a high-fidelity replica rendered on screen. Users interact with the prototype by manipulating the low-fidelity version. This creates visual integration across domains and rapidly increases detail of understanding. The final case is a games controller that requires synchronization across both domains to function. Users freely create their own interface for the controller using buttons that they fix to a physical prototype. Both position and interaction with these buttons are tracked in real time, meaning that users may also physically use the controller to play a simple game and judge its performance. This case shows increased benefits of further integration, where users can seamlessly experience near final product behavior right in the middle of the ideation process. All cases show benefits over current practice, focused around accelerated learning and higher levels of interactivity. Considering interaction between the user and the integrated prototypes, the cases strongly show the benefits of using the digital to simulate behavior and transfer analytic information, while the physical acts as a tangible interface. Considering integration between the physical and digital, the cases show technical feasibility, both of synchronizing models and of updating each based on the state of the other. Higher levels of integration are the enablers for the quicker learning loops that we observe in all cases. However, the technical challenges of doing so are high and must be balanced against the benefits that may be gained. While its methods are not directly applicable to prototyping, the principles of integrated workflow underpinning digital twinning may be realized through immersive realities to accelerate learning and leverage the strengths of each domain simultaneously. This work also highlights several areas for future work. To date, we have little knowledge of best practice, specific forms of value, or how it may be maximized. How we leverage new capabilities is also a challenge in this rapidly developing space. This is compounded by the technical difficulty of implementation. Each of our cases was bespoke and non-trivial, and research should look at how approaches can be rapidly and simply deployed without a large technical overhead. This work has shown the feasibility and value that integrated prototypes may create, but equally underlines that we are early on the path to establishing how we could best use such approaches to maximize value for design. Many thanks for listening to my presentation today, and I look forward to answering any questions.
Hello and welcome to my presentation on our approach for the development of digital twins of smart products based on linked lifecycle information. First, I'm going to explain how digital twins can be used in the lifecycle of smart products. Then I will introduce the Kaiserslautern digital twin modeling framework before giving specific examples of applications of the framework. A digital twin provides a virtual representation of an existing or future physical object. Here, we are talking about digital twins of smart products, which can include their structure, properties, and behavior. In recent years, digital product twins have been used during various lifecycle phases to accompany a product throughout its life and gather valuable information. In our view, a digital twin is not an end in itself, but instead serves a specific purpose. To build a twin for such a purpose, the envisioned use cases and their context must be carefully analyzed and cast into requirements. This is the first step of the Kaiserslautern digital twin modeling framework, which offers a methodological approach for the definition of digital twins. The framework does not prescribe specific tools or methods for the gathering of requirements. However, we have successfully used customer journeys. After the twin's use cases and context have been defined, the actual twin modeling framework supports the specific definition of the digital twin along several dimensions, which have been grouped into overarching, technical, and organizational features. The overarching components include the intended field of application, with immediate or potential application for new business models or for intended optimization during the product's development. Another factor are the reference processes. Similarly, the twin's physical counterpart needs to be defined. Finally, the twin's envisioned lifecycle phase integration should be described in terms of relevant product lifecycle phases in which the product twins are created and how they are used in terms of information technology. After the general components are defined, the framework focuses on the information technology design components. These include factors as network connectivity of the physical twin, data formats, and the twin's envisioned effect on various existing data models. Finally, the organizational design components are defined. These range from the expected user groups to model and data ownership. Finally, role and rights models in the affected software systems have to be considered. The definition of the twin is supplemented by a definition of its required IT infrastructure and interfaces. The framework allows for the definition of vastly different digital twins, which require different implementation strategies. To give a representative example, we provide an approach for the implementation of product data-centric digital twins of smart products, with a strong link to their originating product lifecycle management solution. To illustrate this approach, I will describe the application of our framework to agricultural machines. Initially, we gathered requirements using a customer journey to determine that the envisioned digital twin was supposed to offer information that can be used to predict, prevent, and/or repair damage to some critical components in the machine. All this should work for different configurations of the machine type in question. After refining the resulting requirements, the KDTM was used to define an appropriate solution. In particular, we decided that the existing PLM model should be used to derive digital twins of specific machine instances. Each twin was reduced to the specific configuration of its physical counterpart. Only the relevant components were then used as anchor points for twin-specific data. Data added to the twin component could then be seen in the PLM solution. The PLM model represents all possible configurations of the product in question. To derive a digital twin, only information relevant for a specific configuration was kept. We were able to make use of pre-existing variant management capabilities in the PLM solution for this step. The configuration-specific extract was then reduced to only the service-relevant components, which would later be used as an anchor point for sensor data. Based on this information, the machine status could be monitored. Service processes could be started based on critical threshold values. The service technician could then view a configuration-specific instruction manual during maintenance. In summary, the resulting digital twin was used during the product's usage phase, was centered around the PLM system and also used the PLM system as its central data storage facility. The digital twin modeling framework, of course, allows other solutions, such as using an IoT platform. In order to implement such a solution, a flexible IT infrastructure is required. One possible approach is the semantic linking of product information, as used in our Spider system. In this approach, data from different sources can be linked to a unifying meta-model. The meta-model contains a graph with one node per object in each of the connected source systems. Edges represent existing relations between data objects. New edges can be added to enrich the semantic model. The actual data remains in its original source system and is fetched on demand via web APIs. The combination of the Kaiserslautern digital twin modeling framework, the implementation strategies for product data-centric digital twins, and Spider as a data integration platform are also used in the Accord research project. The project covers a range of different use cases, including automotive work plan management, as well as industrial data analysis in the context of a model of a racetrack. The latter use case in particular showcases the potential of the approaches described so far. Here, sensor data from the racetrack is transferred in real time and combined with pre-existing data models in an Internet of Things platform. The resulting data can then be provided to data analysis processes. You can find out more about how this works and the Accord research project in the talk shown on this slide. In summary, there are vastly different digital twins. The Kaiserslautern digital modeling framework can help you to find a fitting solution for your use case. And the framework was put to use with PLM-centric digital twins. Thank you for your attention, and I'm happy to answer your questions in the following discussion session.
Dear colleagues, my name is Stefan Husung, and I would like to welcome you together with Yannick Koch from Darmstadt to our presentation on a method for the support of the design for digital twin solution and its application on a gearbox system. The presentation is structured in 5 sections. After a short introduction, we briefly present the relevant research questions, the overall approach, and the application of the approach using a gearbox system. Finally, the further steps will be presented. At the beginning, let us briefly introduce the most important terms. This concerns the digital twin as a digital representation of a concrete instance of a real product. Together with a real twin, the digital twin is based on a digital master from product development. An important term in this paper is a digital twin solution, which includes the digital twin and the extension of the real twin for specific use cases. Digital twins are needed to fulfill specific use cases from stakeholders in different product life phases. This includes use cases during production and product usage. On the slide, you can see 2 use case examples. From a product development perspective, one relevant use case, among many others, is to collect relevant usage information of the real twin for the following product development. For the use cases, relevant product properties are required from the real twin, which, among others, are based on state and flow variables. A systematic development of the digital twin solution is necessary so that the relevant product properties can be identified as required. Especially when extending the real twin, it must be ensured that the extension supports the digital twin use cases, but does not impair the properties of the real twin. Against this background, in the paper, the 2 research questions on the slide for the systematic development of the real twin solution are discussed. The presented approach consists of 4 steps. First, the needs of the different stakeholders and the related relevant product properties are identified systematically, followed by loops of conceptions of the digital twin solution and analysis until the goals are fulfilled. One focus during conception is a selection of the relevant measuring principles and sensor concepts.
The presented method is now applied to a two-stage gearbox system. First, the stakeholder objectives and use cases are investigated. The here investigated stakeholder are the process manager and the maintenance personnel. A use case for the stakeholder process manager is the maintenance scheduling. Second, on basis of the use case, maintenance scheduling, the relevant digital twin property, gearbox wear, is identified. A derived requirement is the detection of gear tooth damage. This requirement should be fulfilled by a digital twin solution in the third phase, conceptualization and design. For the presented gearbox system, an effect chain analysis is used to find possible sensor solutions. And these are conceptualized and applied to the gearbox. An effect chain analysis is one possible method to be used in the third phase, but there are also others. In this example, the measurement of the instantaneous angular speed at a gear wheel is further developed, as it needs no change to the power transmitting measurement elements. This figure shows the possible integration of the sensors inside the gearbox housing. In the next iterative step, the influences of the digital twin solution, here the integration of sensors to measure the instantaneous angular speed using a gear wheel as measuring scale, are investigated. For example, a change to the gearbox housing could change the eigenfrequency or even weaken the housing. This influence has to be calculated in order to decide if a change to the gearbox housing has to be applied or if this influence is negligible. Furthermore, the integration of the sensor inside the gearbox could deflect the oil flow, which could cause, in the worst case, a deficient lubrication. To exclude this impossibility, the sensor housing could be used to support the oil flow towards the gear wheel. An interesting question that arises when applying the method is if other use cases or requirements can also be fulfilled by the digital twin solution, or if even new use cases can be created. These new use cases can then be integrated back into the whole digital twin solution, and increased benefits can thus be achieved, which is supported by the systematic study of the influences on the digital twin solution. Concluding, a method for the design of a digital twin solution was presented and applied to a gearbox system. Therefore, the 4 steps: investigation of the stakeholder objectives and use cases, identification of relevant requirements, and conceptualization and design, as well as systematic investigation, were applied to the 2-stage gearbox system. So first, the stakeholder use cases were investigated, and second, relevant requirements, here the detection of tooth length damage, were identified. Then in the third step, a sensor concept to fulfill this requirement was developed. And finally, the influences on a digital twin solution were systematically investigated and also iteratively integrated into the conceptualization and design phase. The presented example was just a glimpse onto the application of the method. The method will be further developed, especially in regard to the influence onto the real twin. Subsequently, it will be applied and evaluated on other examples. Thank you for your attention, and we are keen to discuss your questions in regard to the presented approach.
Okay, thank you for all speakers to hardly work to prepare all those videos. I don't know if we received some question in the chat or not. I don't have any question. Maybe I will launch the discussion with first questions for Fabian Wilking from Erlangen. Is the proposed solution for using SysML to the structuration of the digital twin definition, and is also applicable for the operation of the real system, or it's only on the side of the operation of the digital model?
Yeah, thank you for that question. I think the answer is both, because when we did this small project, we realized that the design of the digital twin becomes very aware. We become aware of the interdependencies between elements and how to construct the digital twin. What our initial motivation was actually, when we create these system models, they often are left unused afterwards. And we were thinking, okay, we modeled all these interdependencies now, and now we have to do something by just looking at them. So we try to utilize them and use them during the operation of the digital twin. And that was in our example very feasible. And I think it's something you can later, with a few more challenges coming up, but that's something you can scale to more complex systems.
Okay, thank you for this very interesting answer. Any additional question?
I think
excuse me, there are some questions in the chat, in the session chat.
Oh. So I don't have access. Okay. I should be back in the list.
So you have 3 options. There are event, my agenda, and session. If you click on the session, then you will have a choice to choose chat.
Yeah. Okay. I'm on. Thanks. Then maybe Stefan, you ask a question for Fabian. Then maybe you can directly ask your question that will avoid me to read.
Yeah, it's fine. I can ask a question for myself. Thank you. But this question has a strong relation. You can hear me?
Yeah.
Yeah. This question has a strong relation also to your question, because my question was, which content do you have in the SysML model? On the slide, for me, it looks like the model was used to control the digital twin. This means when the digital twin accepts or reacts on data. But as Fabian already said, it's also used for the design of the digital twin. So it means it represents also behavior of the potential digital twin. Is it right?
Yes, exactly. I mean, that's also what I wrote in the end. You have to become aware of what you actually want to model, because there are several potentials what you can do, but not. And that's my personal opinion here. But I don't think modeling anything makes sense. We made some good result with modeling the machine learning context, and combine that with their structural elements in the model. But I think some other aspects might not be involved into the system modeling.
Yeah, and my question especially comes from also our paper, because when we use this methodology, we also thought about using SysML for describing the effect chains, and especially there it also could be an application case. Can you hear me?
Oh, sorry,
you catch the question?
I forgot to mute myself. Yeah, I totally agree. I think that was our initial motivation to further utilize these models, not only for describing. I think that's perfect if you design them, but if you leave these models unused afterwards, it's basically a shame that you don't use them anymore. And that was what our report is about. That we try to utilize them. You have to model differently if you want to create them. But that's definitely something you can combine, like designing the digital twin and then further utilizing the models for their operation.
Very interesting, Maybe we also
Okay.
can keep in contact with this. I think also Sandro is online. Maybe we can discuss this afterwards.
Yeah, I suggest you have private discussion for developing your debate and to allow everybody to have opportunity to discuss. I would like to invite some questions for Fabian Laukotka, or because I don't see any question in the chat. Or if not, I will have some question, of course, because today I'm the expert of digital twin.
Yes, feel free to ask. So.
Okay, then first questions about the link between digital twin and PSS. The product and physical dimension of PSS, it's okay. But when you talk about the service, how you describe the service in the digital twin? Or you link the service with the digital twin, I should say.
Yeah,
it's not
okay, the link between product service systems and digital twins. So based on our experiences in the industry, we have here, we identified that especially smaller industries who want to smartify, let's say, their products, they need some aspects like data handling, data gathering, etc. And they face huge challenges doing so because it's a new domain for them. Mostly they've done just mechanical products, sometimes mechatronic products, but the whole data aspect is new to them. On the other hand, digital twins really focus on this aspect, data handling, data gathering, data management, in connection to a real product. That's the main idea of a digital twin, the connection from digital to reality. So the connection there is really, like I tried to explain in the presentation a bit, like we might have the solution for the product servant system challenges, but the solution itself has also some challenges. So it's not like a remedy. We can apply our techniques and ideas, but it's difficult to do so. But the connection is really, they have challenges we are also facing right now. So let's learn from each other.
Okay, thank you very much. Additional question for Fabian, maybe? No. Okay, and how the services to provide associated to the product will be maximized with the smart value of the product, with sensors, IoT, and so on and so on. Then, on your point, it will allow to intensify the sanitization of the product.
I'm sorry, your audio is lagging here. I'm not sure. Does anybody else experience this? I wasn't really able to understand your question.
Oh, sorry, I'm audio. My question was about the intensification or the servicization of product with technology on IoT sensors and so on.
Okay. First, without video, so maybe write it, and I will try to answer it. Any other participants were able to understand it?
I think it would be good to make a relog in. I also had to start my browser again.
I suggest the chairman refresh the page.
Now my browser fully was frozen. I had to restart my browser again.
It seems to be a bit normal.
We already can hear you.
Yeah, you hear me?
Yes, of course. We also hear your clicks.
Yeah, sorry, but because all the video, Stefan, okay, sorry. I was
Fine. I only want you to give the feedback that we already can hear you.
Yeah, so maybe to go ahead, I suggest to Stefan, I think you have some questions for Ben, if I'm right.
Yeah, I think Ben is online. Ben, I think you already read the question. It's a very interesting approach. We know from our verification or prototyping cases that we always have to deal with different versions. You have to make an update, you have to modify something, and it's always interesting how to make both up to date, the real and the digital twin. You can say some words about this?
I certainly can. I think the paper really is I say an exploratory study looking at that spectrum from where the digital and physical models or medium are essentially separate through to them being fully integrated in case 5. And the idea of doing that is to start to understand some of these issues, Stefan. And where we are at the moment with that is at the spectrum of where digital and physical are largely separate. We are looking to have a system working with NTNU called Pro2 Booth, and we built the ontology out for that to effectively capture iterations of the physical and then integrate those. So we're developing the ontology and schemas to integrate those or that with sort of current PDM or PLM systems.
Okay.
But then as you move to the other end of the spectrum that we showed in case study 5, where effectively the digital and the physical are, codependent and co-evolve, the work we are doing at the moment is much more around looking at what paradigm you'd want, what are your requirements for version control systems, and what are your requirements for data capture. And we are currently modifying and adapting sort of GitHub type methodologies, which appear to be more appropriate when as things become more better integrated. Obviously that work, that isn't published in this part of this paper, but that's the ongoing work. So I think we need to be understanding, as they become more integrated, I think where we are at the moment, our understanding suggests that your requirements for data capture also evolve and change. And you move from in engineering, your final product isn't the culmination and continued iteration of your prototypes, whereas in software it is.
Of course.
So we're sort of moving more towards that. And then the question becomes, to do so, how are those requirements changing? What new methods or approaches might you need?
Yeah, I think in this case also the configuration management is very, very important. Which baseline you have to define especially for the virtual twin, and then wait up to the update of the physical prototype. Otherwise, you don't have the same version.
Absolutely, and what I suppose we started out with this paper, although not explicit in the title, saying the question maybe was, with a digital twin paradigm of this integration, how can we leverage that in the earlier stages of design?
Yeah,
and where you get that fast learning, and it's what you've touched on, Stefan. You get very fast learning, so then you get explosion of data, and you can do more. You can understand multiple different configurations, and the attraction of the case study 5 that Chris showed is that the users configure the controller. You move the buttons around, you configure your controller and play the game at the same time.
Yeah,
that learning loop is fast learning,
very dynamic. Yes, of course.
And just to add, sorry, Stefan.
No, I only said it's great. Good idea.
And the apologies for my colleague, Dr. Chris Snider. He can't be with us as he became a father at the end of last week. So that's why I'm fielding the question.
Thank you.
Thank you.
Very good.
Okay, thank you. I hope now I'm lagging less. There was a question for Thomas, but Fabian who asked the question. Then Fabian don't seems to be there anymore, or I'm wrong. Yeah, you are here, Fabian. Good.
I think you have to add him again to the presenter mode.
The other approaches for the modeling concepts, and of course, a huge part of the motivation behind our framework was to bring different definitions of digital twins together, and this, of course, includes the early approaches in the RAMI 4.0 concept. And the second question was whether it's necessary to define the purpose of the digital twin first and other dimensions second. And the answer to this is also yes. Of course, the purpose of the twin is what can make it really, really different. If you have a PLM data-centric digital twin, it looks very different from approaches where the simulation model is the center of the attention. And so, yes, this is what the step in the framework for the overarching design components is for. Both questions are really good, and I hope the answers are satisfactory.
Thank you very much. Maybe we'll switch for able to speak, of course, in correct digital environment. Great experience. Stephen, what about the huge expertise in the Gearbox systems that can be embedded finally in the digital twin solution? Because the Gearbox technology is improving more and more over the years and so on. Then this means we have a lot of knowledge and detailed data on the behavior of the system. Is it on the grid? Is it on the mechanical and material behavior, and so on and so on? Then do you have address in detail this aspect for embedding the information and knowledge in the digital twin, like obtaining a knowledge-based digital twin?
I hope I understood you correctly, because there are a lot of disturbances in the line. As I understood, you ask if you also consider knowledge about Gearbox real behavior in the digital twin solution. Do you mean this?
Yeah, exactly.
Yeah, currently not. Especially in this Gearbox system, as Yannick taught you in the presentation, we focus on the measuring principle. This was our main idea, how to collect the relevant information from the Gearbox, but this could be a very good extension to store also this information in the digital twin, and then, of course, use this information for additional use cases. Currently, we are the only motivation was to collect the relevant information, to perform them, or to do something in the digital twin with them. But this could be a very extent. But currently, it was not the focus of our work. Yeah. Oh, yeah, you have extension. I cannot hear you. I think now we lost almost everyone.
Seems the chairman and the rest refreshed the page.
Yeah.
Jelena, I just wonder if it might be, I think most of the questions have been asked. I don't know whether we could ask any of the people viewing if they have any questions, if they could put them in the chat, and we can then all see the question and try and ask either if it's Stefan or myself or Fabian to answer or respond. If we don't have any questions in the next 30 seconds or minute, perhaps we should think about closing it.
I mean, it's due to chairman, and there are some questions in the chat. So yes.
I think most of the questions are already discussed.
Yeah, yes.
Yes, I had another question for the other Fabian, but I can write him directly. So in case he can't reconnect, that won't be that bad.
For which? For who? For Yannick?
No, for the other Fabian. From Fabian to Fabian.
Fabian. Yeah, that's always good.
Yeah, the name is not that common, so kind of funny that we have two of them in one session. And
yeah.
So again, can I just ask any of the participants, if you have any questions for any of the presenters, including myself, please put them into the chat while Benoit just rejoins.
Yeah, you have a good suggestion, Ben. Thanks.
Yannick, I think we should go also in contact with Thomas, because I see there are a lot of similarities between our approaches.
Yes, that's a good idea, I think.
But we can also do this offline.
So my sense, if Benoit is happy with this and other presenters, is that there aren't any additional questions. We've got a couple of follow-ups between the presenters. If there aren't any questions from the other participants here in this session, maybe we should close at 12:20.
Yeah. If there is no additional question in 1 minute more, we may close this session. I would like to thank all presenters for preparing the video and answer the questions, and also all the questions that have been asked during this session. And I finally thanks all the attendees, and we may close the session right now. And of course, take the opportunity to have extra debate on chat. I already received some invitation on LinkedIn for entering in discussion in the private mode and so on. Then take this opportunity of virtualized conference to share in other ways. And I hope soon we will be able to meet together in real physical events. Thanks all. Bye-bye.
yeah, thank you for hosting.
Goodbye. Thank you.
Bye.